In these slides, we want to find the potential difference between 2 points in a region around a single point charge. So this is similar. We already found what the potential is due to a point charge before in a different way. So this is a nice way of showing the same thing, but in a slightly different way. We're going to make a path between 2 points. So we'll start out with the point charge, and I just put some radial lines outward like this. And we have 2 points in space, point number 1 and point number 2, that are far apart. And we know that the potential difference between the 2 points is obtained by doing this integration. You have to choose a path between the 2 points. Any path will give the same answer. So let's choose a simple path so that we can just do things easily. We don't need to consider a complicated path. In the next file, we'll show you another derivation that will work for any path. And I mean, it's the same thing because we can choose any path we want, but the other file will be a bit more complicated. In this file, it's the easy way of doing it because we can just choose to move from point 1 to point 3, moving always perpendicular to the electric field. That means we're moving on an arc of a circle. So if you move on an arc of a circle perpendicular to the electric field always, then the potential at 1 is the same as the potential at 3. Remember, we talked about this idea before. So basically what we want then is the potential difference between 3 and point 3 and point 2. It'll be exactly the same as the potential difference between point 1 and point 2, because the potential at every single point here is the same. So basically then what we're after is the potential difference between point 3 and point 2 along this line, radial line going outwards. And that makes the derivation a bit easy to do. So integration of E dot dr becomes integration of E dr because the electric field is pointing radially outwards and the displacement that you're moving is also radially outwards, dr vector. So the angle between them is 0. So we got rid of the dot product. Instead of E dot dr, we got E dr. So that makes things easier. And we know the electric field due to a point charge is kq over r squared. So you get integration from point 3 to point 2, kq over r squared dr, which is a very easy integration to do. So the kq go outside, and you want to integrate basically r to the minus 2 dr. And so you add 1 and you divide by the total power, which is r to the minus 1 over minus 1. And then you have to substitute the upper limit and the lower limit. The minus sign, I'll take it outside. And then you have to substitute. You get 1 over R2 minus 1 over R3. And if you just bring the minus sign inside and reverse the order of these terms, you get KQ 1 over R3 minus 1 over R2. And of course, R3 is the same as R1. The distance from the charge to point 3 is the same as the distance from the charge to point 1. So I can replace R3 by R1. And that gives me then the final result I want for the potential difference between point number 1 and point number 2. It's basically KQ over R1 minus KQ over R2. And so it agrees exactly with what we took before for the potential difference between 2 points. And so the potential difference then between any 2 points due to a point charge, when there's a point charge in this region of space, no matter what path you take, we know that it should be independent of the path. So whatever path you take, it will just be kq over the first distance minus kq over the second distance. If we want to get the potential at a point, taking the potential at infinity to be 0, so we can take point 2 and take it all the way to infinity. If you imagine taking this point right here and moving it all the way to infinity. Now V1 minus V infinity, we're going to take the potential at infinity to be 0. That's the same convention we used before to make the potential at infinity 0. And if you put kq over R2 with R2 going to infinity, this becomes 0. And so you get that the potential V1, the potential at point 1, is equal to kq over R1, which is exactly the formula for the potential that we took before in the case where the reference of potential at infinity is 0. The potential at infinity is 0. So everything is working fine, and we got the same result as before, but now using a path integral.